Okay, so this will be over the beginning, the first part of the information in chapter 2. And I'm going to give the examples of, this is actually kind of the basic chemistry and the inorganic chemistry. And then I'm going to record a lecture which talks about the organic chemistry. So inorganic chemistry would include things like acids and bases and salts, and it would also include properties of water, that kind of stuff. When we start talking about organic chemistry, those are like molecules that you find in your body. So like proteins and lipids and nucleic acids and carbohydrates, that would be all organic. And one of the things that distinguishes inorganic from organic is the abundance of carbon, right? So carbon is extremely abundant in organic molecules. It's the skeleton of the organic molecules. Whereas if we're looking at an acid like hydrochloric acid, which we'll talk about, hydrochloric acid doesn't have any carbon in it, okay? So the organic chemistry, I'm going to record that lecture and I'll have it posted by tomorrow at the end of the day. I'm going to record it. Okay, so when we look at chemistry, it's important to realize that we are, like all of matter, composed of chemicals, right? And we are specifically composed of atoms. And in the lecture, I talked about some of the most abundant atoms. And what was the acronym that I used? Schnapps, right? Not the liqueur, right? But schnapps. Right? So those are some abundant atoms that are in our body. Now, these atoms have particular properties associated with them that make them very reactive with one another. And so when we start to talk about compounds, which your textbook uses, but I use molecules. So compounds and molecules I kind of use interchangeably. You actually kind of do that in biology. Chemists, however, are very, very particular. Molecules have to be all the same atoms. So like you could have a molecule of oxygen gas, right, which would be O2. Whereas compounds would be where you have different atoms attached to one another. So when we look at compounds, this is different atoms bonding together. So for example, I gave the example in the lecture of glucose. Does anybody remember what glucose is? What's the molecular formula for glucose? Awesome. Okay, so what this means is that we have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms, right? These atoms are molecularly bonded to one another, which means that if you break those bonds, energy can be released. So it took energy to build the bonds, and then when we break the bonds, energy are released. Energy would be released. In your book, in this chapter, they actually have this really cool diagram that shows the percentage of the different atoms or elements, and I'm using atoms and elements kind of interchangeably. An element is made up of all the same atoms. That's not really something you need to know, but if you get confused, that's what it is. So, for example, oxygen, carbon, hydrogen, nitrogen, and then I skipped over some of the minerals like calcium and potassium, and then I included in my schnapps phosphorus and sulfur. Okay, so if you look at this, about 65% of our body is oxygen. All the atoms, if you look at the percentage of atoms, we don't need to know those percentages, but it just kind of is an interesting diagram that shows what are the most common atoms that we have in our body. Now, if we look at the structure of an atom, we can talk about the nucleus. So in the nucleus of the atom, and that is the center, not to be confused with the nucleus of a cell. So nucleus means nut. So it means the center portion. Okay, so don't get confused. I'm thinking, oh, well, my geek cell had a nucleus. But no, this is different nucleus, right? Just the center. So the nucleus has in it protons and neutrons. One of these is positively charged. Which one do you think? Protons, right? Because you get, oh, well, P, that's a good giveaway. But neutron, neutral, right? So they're named neutrons because they have no charge, they're neutral, okay? So we say that the protons have a positive charge. The neutrons, I'm just gonna put like a little 0 here. They are neutral. And by definition, these have 1 unit of mass. So I'm gonna put 1 unit of mass. 1 unit of mass. Okay. So that's the nucleus. Now, I read an analogy once that said, like, if I was the nucleus of an atom, and let's say I'm a bird, let's say I'm a little crow, and if you try to figure out where the electrons are in relationship to me, they would be like 2 miles away. And so the electrons are in orbit around the nucleus, but most of the atom is simply space, right? So there's a lot of empty space in the atom, okay? So we have what are referred to as the orbits. And in the orbits, we have electrons. So way far out, if you scaled everything up to the crow and the 2 miles away, right? So the electrons have a negative charge to them, and they are so small that we say that they have no mass. So there's different ways to visualize what an atom looks like. And remember that this is not something that you can see with your own eyes. This is something that we use technology to figure out what atoms look like. And so if we look at a diagram, this is the helium atom. So in the center would be the nucleus, and that's where the protons and neutrons are. And then this just shows the orbit. And this is one way to visualize it. And this is a 2-dimensional way to visualize it. And so this is the easiest way to draw, right? So if I was to draw what an atom looks like, and I'm drawing on this paper 2-dimensional, that's the way it looks like. But really, probably what an atom more looks like is a ball, right? So it's 3-dimensional, right? So this is the nucleus, and then we have this cloud, and the electron just kind of moves around, and it could be found at any particular point in that cloud. And then there could be another cloud of potential electrons further out, okay? So that's the 3-dimensional model, is showing it more like a ball, right? Okay. So when we look at the different elements on the periodic table, we could look at, let's look at helium first. Helium, so He stands for helium. Helium is not an element that we have in our body, right? And there's a reason for that, and I'll explain that in a second. But then we have, down here, we have 4, and then we have a 2 up here. Sometimes the 4 is right underneath the symbol. Sometimes it's off to the side like I've drawn it here. Okay. So we say that this one has an atomic mass. This is the atomic mass of 2. And the atomic mass by definition, atomic mass by definition is the number of protons. And then down here, we would say that this is the atomic weight. Oh, sorry, what? I'm sorry. Sorry, I knew I was doing this wrong. This is the atomic number. I said that and I'm like, this is not right. Sorry. Cross out mass, say number. Okay, atomic number. And this is the atomic mass, sorry, or weight. So this would be the weight. Okay, so what does this mean? This means that there's actually 4 subatomic particles in the nucleus. If I know that there are 2 protons and the total weight is 4, then how many neutrons must be in my nucleus? 2, right? So this would be the number of protons, and then you would figure out that the number of neutrons by this number. Now, these mean that the number of protons and neutrons are the same, and that is true for a lot of the elements, but we're going to talk about when it's not true. And when it's not true is when we have different forms of the elements that are called isotopes. Okay. Now, this element does not have a charge. So how many electrons must this element have in order to balance out the charge of the protons? 2, right? So these numbers give us a lot of information about the atomic structure of the molecule, or excuse me, of the atom, atomic structure of the atom, right? How many protons, how many neutrons, how many electrons. And so if I were to draw this, right, I would draw 4 subatomic particles in the nucleus, and then I would draw a shell around there, and then I might put my electrons equidistant from the nucleus and equidistant from each other. So I put here, here, and I might put a positive, and like a 0, 0. Okay, so that tells me that there are 2 protons, 2 neutrons, and 2 electrons. So we're going to have practice with this in just a minute, where I'm going to have you look at these numbers and then figure out what is going on in terms of the atomic structure. Okay, so this is our periodic table, and so this is what has the information about all of the atoms and elements. So, for example, you could look at carbon. So carbon has a 6. And it weighs 12 units of weight. And so you would know that it has 6 protons, 6 neutrons, and 6 electrons. So this information is what you would get out of a periodic table. Okay. So I would always give you that information. I would not make you memorize the atomic number or the atomic mass. Okay. So when we look at isotopes, isotopes are atoms that have the same number of protons. But a different number of neutrons. One of the isotopes that probably have heard of is an isotope of carbon. So if we look at carbon, it can either be this form, oops, sorry, 6 and then 12. It could be this, right? So this is what is normally found. And it is the most stable. So it's the most abundant. So it's the most stable. Okay. So this would have equal number of protons and neutrons, and you would know that because you could add them up, right? Got to be 6 plus 6 equals 12, okay? But what if carbon was this? Okay, this is an isotope of carbon, and sometimes it's called carbon-14. And what do they use carbon-14 to do? Yeah. Yes, so they find the age of a rock, or it would be bone, of a fossil, right? Or of a bone. So it's kind of interesting because, and you don't need to know this part, but in the atmosphere, carbon-12 gets converted to carbon-14. And then we actually take that carbon-14 and we put it into our bodies, we put it into our molecules. And it's relatively constant. So it's about, our carbon-14 in our bodies is the same concentration as the carbon-14 is in the atmosphere. And then when we die, we stop taking this up. and it starts to break down. And so this is unstable.
C14 is unstable?
Yes, it's unstable. And so it will break down over time. And so the relative amount, say I find a bone and I think it's 10,000 years old, if I looked at the amount of carbon-14 in there, then I could estimate the age by looking at the relative amount of carbon-14 to carbon-12, right? Because it breaks down over time. Also, these, because they're unstable, they emit energy, and they are referred to as radioisotopes, right? Because it emits a little bit of energy when it is present. It's got stored energy and then it'll start to emit energy. So carbon-14 is an isotope of carbon-12, of carbon. Right? Another example that we have is hydrogen. And so hydrogen is a really interesting atom and element. So okay. Hydrogen is this. How many neutrons do you think a normal hydrogen atom has? How many neutrons? No, because it would be like, there should be one, there should be a 2 down there, right?
Okay, so it'd be like
So if its atomic number is 1 and its unit of mass is 1, then there's no neutrons, right? And so if we were to look at a hydrogen atom, we have in the nucleus a proton. And then surrounding this, we have an electron. And so sometimes they don't even call this an atom, they call it a proton, right? I mean, they just say it's not even, because it doesn't have any neutrons in it. Okay.
Is that the reason it only have one electron circling it?
Yes, it only has 1 electron because these balance themselves out, right?
Right.
And then if it gets rid of the electron, then it's a proton. So this, we'll see this. So if we see this H with a plus, that means it's a hydrogen with a positive charge. So this has lost its electron and is now a proton. A proton, I ran out of room there. Proton, okay. So if it loses its electron, I'm sorry, that's still hydrogen. If it loses it and has that positive charge, it's an ion, and it's essentially just a proton. Okay, that'll be significant when we start to talk about acids and bases. Because what an acid is something that gives off and releases hydrogen ions into solution. Okay, so we can also see that sometimes hydrogen exists in this form and also in this form. Oops, there's a 3, should be a 3 there. Okay, so it can have one proton and 1 neutron. This one actually has 2 protons, excuse me, 2 neutrons and 1 proton. Okay, so it has 1 proton, but it has 2 neutrons. This emits energy, right? And it's kind of interesting. This is actually, you don't need to know this. This is called trillium, and this is called deuterium. And if we look at some way that they use this is a radioactive isotope or a radioisotope. Sometimes they put that isotope in watches. Oops, do I have that picture? Here it is. So the reason why this watch, this is a Swiss Army watch, the reason why this watch glows in the dark is because there are trillium atoms in there that are emitting energy. They used to use, I think, radium, but they discovered that that is really high intensity energy, right? And that's not something you want near your body, right? Or your head, if you're sleeping with it. Okay, so if we look at those isotopes, this is in your book. So we have the protium, okay, this is just normal. This is the deuterium, and this is the tritium, okay? 2 neutrons, 1 proton, 1 electron. Okay. So those two, the deuterium and the tritium, are considered to be isotopes of hydrogen. Okay. The last thing I'm going to mention before, I want to talk about this. So we can use isotopes in medicine. And the reason why they're so useful is because they emit energy and they can be used to track the movement of molecules in the body. Okay, so they emit energy and used to track movement of molecules in the body. So one that is commonly used is nitrogen and also iodine. Let me get this right. So nitrogen is N13. Nitrogen normally has 12 neutrons. Here it has an extra neutron. And then iodine, 123. These are odd numbers, so you know that there has to be not the same number of protons and neutrons. What gland in our body requires iodine? Thyroid, right? So the thyroid gland is actually why we have iodinized salt, right? We put iodine in our salt so that we make sure that we get enough iodine to produce thyroid hormone, right? So radioactive iodine can actually be used to treat thyroid cancers, right? And then nitrogen can be used to label molecules, and then they follow these molecules through the body. So in your book, they talk about the type of scan, which is called PET, P-E-T. And so PET is short for positron emission tomography. And I would never make you spell that out, but that's PET. And so PET looks for radioactivity in the body after you have put radioactive atoms or molecules in the body. And so one image from your textbook looks like this. And so what they have done is that they have radioactively labeled glucose so that they know where glucose is going to in the body, so that they know where in the body a lot of energy is being used. So these would be areas of really high cellular metabolism, so lots of breaking down glucose and producing energy. And so that actually suggests that these cells are using a lot of energy that could possibly be cancerous. So they could possibly be cancerous because they're using so much glucose, so much energy. They're using the body's reserve of energy. And so this is a PET scan.
Was it Ben used to do this?
You know, they call it, if you go to like the hospital, what do they call it?
The PET scan is what they do. They only
Yeah.
have it on Wednesday.
So they call it, this is nuclear medicine, they call it. So this is an example of nuclear medicine, right? Yes, they are using radioactive atoms, which are emitting energy. And so they carry them around in cases that prevent radioactivity from leaking out, right? And so yes, I mean, like if people like open up the case and like, I don't know, got a hold of it, it could possibly cause problems. But generally, when they put it in the body, it's at such low amounts that it doesn't actually cause problems. But yeah, you can get a lot of it, right? And they actually have to make these radioactive atoms. So, I guess there's a place up in Canada that is, that makes most of it for like the whole world. And so their facility could possibly leak radioactivity because they're making so much of this radioactive atoms for the use of medicine, for use by medicine. Okay, so are there any questions about isotopes? Yes.
Mine's about like the protein, so they put the iodine in you when you do these. So do they also do that with MRIs and stuff like that?
No, that's different. Yeah. Yeah, that's doing a different test. Yeah, looking at something different. Okay, yeah.
Will there always be more neutrons in the
Isotopes. Yes. So the reason why the number is higher, like you wouldn't have, so the normal is 12 neutrons. In the radioactive form of nitrogen, there is an extra one, and so that's why it's called nitrogen 13. And so it's unstable, and it's going to want to give up a neutron, right? It's going to want to get rid of that neutron. And so when that neutron leaves, it has to go someplace. And so that those neutrons coming off of the atoms is the energy, right? And so that could possibly damage genetic material, and radioactivity can lead to a breakdown of the genetic material and possibly cancer as well. Okay, so those are isotopes. Okay, so the electrons can move from one shell to the other, and also the number of electrons in each shell determines the reactivity of that particular atom. So if we look at the nucleus, this is my nucleus, this is my shell, and I'm just going to draw half the shell, and it's going to look like this, okay? So there's 3 shells. So this is the nucleus, and these are the electron shells or electron orbits. Okay, so if I have an electron, I'm going to get a different color. Can I get a different color? Compare colors. Purple. Okay, so if this is my electron, it is negatively charged, and so it is going to be attracted to the nucleus. So it's kind of like a magnet. I like to think of it as a magnet, so that I can put energy into this atom and cause the electron to move away. So imagine you have 2 magnets, right? And you put energy into it and you move the electron away from the nucleus, okay? So it could jump up to a higher orbit, okay? So if it goes in that direction, that means that the atom is absorbing energy. So I would say this is absorbing energy. And it can be stored, right? It's stored energy. And it can be used, right? So if I move the electron further away from the nucleus, I'm storing energy in the atom itself. Okay. The electrons can go the other way. So I could have my little electron here, and it could go back towards, right, the nucleus. And that means that I am releasing energy. Releasing energy. And this is really important because electrons move closer or further away depending upon what two atoms are bonded to one another. So we start talking about chemical bonds, which are two atoms that are linked together and might be sharing electrons. Then you have stored energy in those chemical bonds. And when you break those bonds, oftentimes the electrons will move and energy will be released. So that's one important part of the behavior of electrons. The other is that we have these shells that hold different numbers of electrons. So this first shell has a maximum of 2 electrons. Okay, so it can only hold 2 electrons in that first shell. The other shells can all hold 8. And sometimes this is referred to as the octet rule, because octet means 8. So besides that first shell, all the other shells can hold 8. Now, the outer shell is super important, and sometimes it's called a valence shell. But what I want you to know here is the number of electrons in the outer shell or orbit determines the properties of the element. Okay. So in reactive elements or reactive atoms, the outer shell is not filled. So what that means is it wants to either share or give away electrons or take electrons from it wants to, the most stable atom is one that has all of its outer shell filled, right? So it has 8 electrons in its outer shell. So if it is not reactive, it is said to be inert. Okay. And inert atoms have their outer shell is filled. Okay. So the best example is one that I just already gave of this last one, would be helium. Let's see, helium's got 2 protons, 4, okay. So how many electrons does helium have? 2. So that means that its first shell, which is its only shell, is filled. So what do they call helium? That's not laughing gas, that's nitric oxide. That is what is in the balloons, really light, it makes your sound funny. Okay? Helium is called a noble gas. Right? Meaning that it does not interact with anything, right? It's noble, it's far above interacting, right? Okay, how about carbon? How many electrons is going to be in its outer shell?
2.
Not 2, because 2 is in the first one.
Oh. 6.
4, right? Hello. Yeah, I'm sorry. No, it is not. Okay. Don't kick it. No, I don't think so. So remove it. Okay. It's been here for a couple days.
Oh, it has?
Yeah, it has. Okay, thanks. So carbon has its nucleus, right? I don't think that wasn't a bomb, hopefully. Here's the, right? We have 2 electrons, and then we have 4 electrons, right? Okay. So so carbon, is its outer shell filled? No, carbon's outer shell is not filled, right? So that means that in order to fill carbon's shell, it would like to share 4 electrons with other atoms, right? So carbon would like to get some more electrons and share them with other atoms. Okay?
Because it's trying to go for 8, right?
It's trying to go for 8 because 8 is the most stable. So this is one of the reasons why carbon, right, is so such a good molecule for building organic molecules is that it will share, right? And it tends to share in a symmetric fashion. If you have 4 here, and you can put hydrogen, 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 and you would get a molecule that looks like this. Right? So what that means is that carbon likes to share, right? It's sharing the electrons with those 1 hydrogen. Hydrogen is now really happy because it has 2 electrons, right? Because it's sharing with carbon and it's got 1. And so does anybody know what this is? It's CH4. Does anybody know what molecule, what is this called? Close. Well, this has got a name called methane. Okay. So this is methane gas. Right? CH4, methane. Okay. Methane gas, is that energy? Can that be used as energy?
Yes.
Yes. And so what you have done is by sharing electrons, is that you have stored energy, right? And so when you break these chemical bonds, then it releases energy and you can burn methane, right? And it releases heat and light, right? So you've stored it by having the electrons. So if they're here, they're going to move a little bit out. That's going to be storing. And then if I break that chemical or bond between the hydrogen, then it's going to move back in and energy is going to be released. Wow. Okay. So I have kind of a funny video, and it's kind of, I love that the fact that it was produced and released by the European Union on the chemical party. And so what they have done is they have kind of dressed people up and are having them act out the different elements, okay? So, and unfortunately the music is kind of bad, or it kind of adds to the whole party element, I guess.
Can't get it now. Can't get it now like can't get it now. Can't get it now like I'm gonna stop. Let's get it started. Can't get it now. Can't get it now.
Okay, that's the European Union. Okay. Don't want to watch that again. There we go. Okay. Okay, so I have a little sheet, and I want you to practice drawing some atoms. So you can work with somebody, or you can work alone. I'm going to turn the lights on. Okay. This has a front and a back. So I want you to answer both questions based upon what we just learned about atoms and their structure. You want me to pull that back up there?
No,
Did you take notes?
Yeah, we got a question.
Okay.
So if Harvard has 6 and 12, right?
Yep.
And then you draw it over here, why does it only have 2 atoms shown on box?
Okay, so it has 6 protons.
Protons,
Those are positively charged.
right?
If it is neutral, how many electrons does it have?
6.
6.
Which means-
So there's 2 and 4. 6. Yep. Neutrons have weights.
Because
They have no charge. So you wouldn't have 12 electrons, you only have 6.
6. So the 2, because shell can only have 2, you have 4.
Yeah.
No.
So,
Say how many, electrons you just have to fill the second shell. So, you need 6. Yeah. Because it says fill the second shell. If it was something that this is for the third shell.
Oops. Okay, so let's look at oxygen. I'm not going to draw it, but you would have drawn how many protons and how many neutrons in the nucleus? How many? 8. So 8 protons. How many neutrons? 8 neutrons, right? So you would draw them. You could draw them as little circles. You could put a positive and a 0 in there. And then how many electrons?
2 in the first shell
2 in the first shell. So I'm just going to write 2 here.
and 6 in the outer shell.
6 in the outer shell. Now, how many electrons would it need to share in order to complete its outer orbit? Second orbit. 2.
2.
2. So the answer is 2. Yes. Yep. 2 makes it 8. So when we look at oxygen, oxygen tends to form, like if we look at oxygen gas, we'll talk about this, but oxygen gas is 2 bonds. It looks like that, right? So this would mean that sharing 2 electrons with another oxygen atom. And so that would make both of them have their outer orbit filled. Right? 2 bonds, 2 chemical bonds. Okay. So that is oxygen gas. Now, just looking at the silica or silicon, this is not an element, this is glass, so this would not be an element that we have in our bodies or in organic molecules. But how many electrons are in its outer orbit? 4, right? So it has 2 in the first orbit, 8 in the second orbit, so the second orbit is filled, that's 10, right? And then 4 in the outer orbit. So it is very similar to carbon. So that's why science fiction writers say, oh, we could have life based upon silicon and not based upon carbon, right? So it is going to be very reactive. It is going to want to form bonds with other atoms. Okay. Any questions about that? Yeah.
So I guess I'm gonna get it. Can you draw it out what it looks like, I guess?
Well, you would have, so it's got 14, so it'd have 14 little circles with a positive in them,
All positive?
and then
7,
14 little neutrons with a 0,
Okay.
because its weight is 28,
Oh, gotcha.
right? So it'd have 14 protons,
14.
14 neutrons, because it weighs 28,
Okay.
but it has to have 14 electrons. So 2 plus 8 plus 4 would equal 14. Okay. Okay. Okay, so the last thing I'm going to do today is I'm going to talk about the different types of bonds. Okay. Okay, so you might have seen ionic before. What this means is that an ion is a charged particle. So when we're talking about ionic bonds, this means that electrons have actually been exchanged between atoms. So this is the exchange of electrons. And it could be just one, so I'll put electrons. between atoms. And you can imagine like how reactive that would be if an electron leaves and gets put to another entire atom. But that might be very energetic, you know, it might be a real energy release. Okay. So a good example of this is sodium, the best example, especially biological, right, is sodium and chloride. Okay. Notice how these do not have charges. These are elemental sodium. So if you just had only sodium atoms, right, and only chloride atoms, this elemental sodium is a metallic silver. You will never see this. Like, it's not like something you will dig up, right? It doesn't exist, really, because it is such a reactive atom, okay? So it's not going to want to exist. It's going to want to react with other things, okay? This is a yellow gas, okay? You're not going to see this just out in the middle of nowhere, right? Yellow, so chlorine gas is toxic, right? So when you combine these two things, what you get in the chemical reaction, so I put a little arrow there, is you get sodium ion plus a chloride ion. Oops, not plus, sorry. Oh, sodium chloride. There we go. There we go. Sodium chloride. So if an ionic bond is an exchange of electrons, is it the sodium or is it chloride? Which atom of these actually gave up an electron? Sodium, right? Because now it's positive. So in order for it to be positive, it had to give up a little bit of negativity, right? This one got an electron, right? So if we look at this, this is actually table salt. And you're like, oh, well, table salt, that's pretty inert, right? So once they exchange just one electron, it is stable. Okay. So if we look at that chemical reaction, oops, wrong way. Okay, this is metallic sodium. You wouldn't want to touch it with your bare hands, right? You wouldn't want to breathe this, right? You put them together and it produces this like this, right, chemical reaction. And then what is actually happening is that you're getting the exchange of an electron. So if you were to go into the periodic table and figure out what the atomic number and the atomic mass would be, you would be able to figure out that sodium has only one electron in its outer orbit, right? So it is going to be super reactive because it is not stable at all, okay? This chlorine has 7 in its outer orbit. So these, when you put those together, the electron simply jumps from one atom to the other. And then it forms a bond because they are negatively and positively charged, so they're attracted to one another. So what you get is like a crystal formation, where like this would be like a salt crystal, you know, your table salt. This is what table salt is, right? This should have a little positive on it. I don't know why it doesn't. That should be a positive. Okay. So that is the ionic bond. Okay. Covalent bonds. Covalent bonds are where electrons are shared between atoms. So these are the bonds that I have been talking about, as in, for example, oxygen gas. When you see a molecule drawn out, these are designated with a solid line. Right? So sodium and chloride, oops, this would not be, so don't write this down, but you would never see this, right? No, right? They just are put up next to each other and their charges are shown. That's why we draw that. This is not covalent, okay? Because they're not sharing electrons, they've actually transferred electrons, okay? So for example, you could have, and I'm gonna use the, what do I use? I'll use methane. So we already drawn this out. Right. So this is methane. So that is a covalent, those little lines represent covalent bonds. Okay. Now, covalent bonds can either be, so if we put types of covalent bonds, they can be polar, and polar means that the electrons are shared unequally. Or they can be non-polar. So think when something's polarized, right? There is like opposite charge of the particles, right? And there's like energy in there. When they're non-polar, right, everything is shared equally, right? So electrons are shared equally. Okay, this example right here, that is non-polar. Because the hydrogen atoms are equally distributed around the carbon atom, and there's no like positive side of the molecule and negative side of the molecule. So it's non-polar covalent. Okay. The best example of polar covalent is water. So if we have H2O, this is water. Okay. Those lines mean that it is a covalent bond. But if you remember that oxygen has lots of protons in it, right? So it is going to tend to pull the electrons to its nucleus. So I'm going to put that it has a negative charge to it. And the hydrogen is going to be a positive charge. And that's just simply because, let's say it's a stronger magnet. It's pulling the electrons. And so we have an unequal distribution of charge. So we would say that this bond right here is polar covalent, okay? Because of that different distribution. Okay. Now, the last bond are hydrogen bonds. Hydrogen bonds are weak attraction between molecules. So they're much weaker than the other types of bonds, and they're designated with a dotted line. So, for example, we have between water molecules. So if I draw my water molecule again, and I'm going to draw two of them. Okay. So between the water molecules, there's a weak attraction. Right. So actually, let me draw that dotted line down lower. Okay, so this is negative. There's a weak attraction. So anytime you see a dotted line, that is a weak attraction. It doesn't, in this case, it's hydrogen, right? It doesn't have to be with hydrogen. So in case of like proteins and the way they fold, or the DNA molecules in the way that we have two strands and there's dotted lines between the two strands, it doesn't have to be hydrogen. It's always just a weak attraction between oppositely charged parts of the molecule. So if you took pot of water and you put it on the stove and you left it there, and it all turned into gas, which bonds are you breaking? Hydrogen bond, right? So this is weak, right? So when I boil water, I never break these, right? If you broke those, you'd be like, right? Be like energy released. Be like fire, right? So you never break these, you break these. And so water gas is just these floating around, right? Because you've broken that weak bond, okay? So you can break hydrogen bonds by putting heat into liquid water and turning it into steam. Okay, so I'm going to stop there for today. And I will record another lecture for tomorrow. So if you have time to look at it before next Tuesday, that would be wonderful.
Is that,
What?
you're recording one today for tomorrow?
Tomorrow. I'm recording one tomorrow, and I'm going to post it tomorrow.
Is that for next week? though?
Yeah, for next week. Yep. Specifically, we're going to be looking at pH, acids, bases, so you might want to read up on that in your book.
Are we turning it?
No. So all of those handouts you're going to study, right? You're going to keep them in your book with your notes, your lecture notes, so you can study.